start, and I'm told that at 12 there is the postdoc seminar in which Alexi is speaking. So if I get lost in time, please remind me that I need to shut up. All right, I put on the board the removal of singularities that we had in dimension in one variable because, well, two reasons. One is I'm going to quote results, state results about the multivariable. Okay, so we saw that if you remove a set of dimension 1, notice the number 1, this will play a role later. And you know that f is continuous everywhere, but k differentiable outside the set of dimension 1, then it's actually k differentiable like holomorphic everywhere. And if you remove one point, which is dimension 0, of course, here L is just a singleton, then you can replace, or you have to replace, sorry, you can weaken continuity and replace it by boundedness. And then we know that it can be extended. I wrote it is differentiable at Z0. So it's removable. And in the unbounded case, we basically know, well, the limit is infinity, and then we have a nice description of it. So notice that this function is what we call meromorphic. It's a quotient of two analytic functions in a neighborhood of 0. Now, I put a question last time on a different situation that by now I have an answer using after talking to Sergey. So I just let me mention it because it's nice. It will be explicit. We put on the problem. I put on the problem that what if f is k differentiable, let's say it's outside whatever, -1, 1 or -1/2/2 is k holomorphic on some open set on the unit disk, let's say -1/2/2 and bounded. And I noted that from what we know by O minimality, there should be a limit in all the points when you approach here, and there should be a limit when you approach here. But it wasn't clear whether the fact that you have like an annulus outside on which it is holomorphic should imply maybe that these two limits should be the same. So it will be continuous. So the answer is no, you cannot remove. And here is you cannot remove this singularity. And the reason for that is the following example. So first, consider a square root function. I'll say exactly what I mean. From C minus the positive, so on a slit plane, consider a square root function. By this, in polar coordinates, I mean r theta goes to square root of r theta over 2, which makes sense here. And it takes, when you approach 1, you will go to a -1 when you do that. But of course, it will not be continuous. You cannot extend it to the positive reals, because here it takes the value 0 as you approach, but here it takes the value -1 as you approach. And now we just want to translate that, to transfer that to this kind of picture. And now you just use a Mobius transformation sending 0 to 1. So now, right, so this is for theta between 0 and 2 pi, not equal, and it's holomorphic. So this is 1. And 2, you just get a Mobius transformation sending 1 to infinity and fixing 0 to C, defined by sending 1, to infinity and 0 to 0. And for example, not this one, Z over Z -1. It will take the whole line to the interval. Sorry, it will take yeah, it will take, yeah, it takes 1 to infinity. So you take the interval to 0 infinity, and its inverse is w plus 1. And now you push forward the square root function using, I guess, this function, right? You push forward the square root function using sigma inverse. So now you define f of z or f of w to be sigma inverse composed with h square, composed with sigma, which will look like square root in this sense, w plus 1 minus 1. And if I'm not mistaken, this function exactly will be defined on the whole, actually on the whole of C minus the interval 0, 1. So this is f of w, and it's defined on the whole, on the complement of 0, 1, and it's bounded actually on the interval 0, 1, but it takes different limit points when you go from here and here. So you cannot strengthen this. You cannot keep somehow L of dimension 1 boundedness just with boundedness, even if everything is nice around the set you removed. Okay, so this will be an example of a set exactly which is holomorphic on C minus the interval, bounded but cannot be extended. All right. So now I'll talk a bit on functions of several variables, and now it will be mostly listing definitions and results. So again, I work in an arbitrary or minimal expansion of a real closed field. But if you're interested, you can think of the reals now. Yeah, we're moving beyond one variable. So when we were at the beginning looking at this, it was an issue. What would be the best definition of differentiability in several variables? And it turned out that what I will write now is enough. And at the end, it will be equivalent to other definitions, but this was actually what we worked with. So always this is open. Now it's in like Cn or Kn, f from u to k. And I will now only be concerned with differentiability on a whole set. The results, some of it might work at a point, but we are less interested what happens by differentiability at a single point. So f is k differentiable or holomorphic on u if for every a1 to an in u, if one f is continuous, so everything is definable. F definable if f is continuous, first of all, and I'll say something about this assumption. F is continuous, and for all a1 to an in u, and for all I from 1 to n, f is holomorphic in one variable, in the ith variable. So f a1 ai minus 1 z is k differentiable in one variable, right? In one variable. So it turned out that most of the proofs even that they were doing really somehow worked nicely. You can think of that as a continuous family of one variable holomorphic functions in all directions. All right, and this is the proof, the definition we worked with, and I should say that over C, this is known. This is known, actually, I'll say in a second, much stronger is known to imply that f as a function of several variables, of n variable, has a power series expansion in a neighborhood of every point. So it's what's called analytic in the classical setting of every A. But in fact, there is a strikingly strong theorem in complex analysis of several variables. It's true even if you remove continuity. This is Hartog's theorem. In fact, by the Hartog's theorem, it is enough to assume what they call separately holomorphic functions. You just need to assume holomorphicity in each coordinate and you get everything from that. You don't need, you can remove continuity from this assumption. Can eliminate continuity in the definition, and it's still true. Okay, so Hartog's theorem says that if you have a function on an open set in several variables, which is holomorphic in each variable separately, then it is analytic function. Analytic in what sense? In the sense of having a power series expansion at every point. Okay, so we allowed ourselves, so I don't know the answer whether without continuity, just definability and separate differentiability, will this be enough in arbitrary or minimum structure to get differentiability? I don't know the answer to that. Okay. And now coming back to our setting, it is a fact that for f in Kn to K definable, of course, this is over C. Yeah, over C. Definable, and I'll write it, I'll add it. I'm not sure if you need it or not, but let's say R differentiable. So it's differentiable in the sense of the real closed field. Then we have like the Cauchy-Riemann statement, F is K differentiable on U if and only if the Jacobian, seeing as a matrix in R to the 2n, is in fact a K matrix. Or said differently, the real Jacobian of F at A, right? The R Jacobian of partial real function, viewed as a map, as a linear map from K to the n to K to the n, rather than R to the 2n to R to the 2n, is K linear. So this is like the Cauchy-Riemann condition. It means that the matrix looks like a matrix of a linear function with K coefficient. All right, so now I will start listing, I'll keep this, properties which we prove for that, which we will need, well, they're important by themselves, but also I might need later when I talk about analytic varieties. So here are some basic properties of k differentiable functions in several variables. Here is the version, the multivariable version of the identity theorem. Assume we have f from u to k, again u is in kn, which is always definable and k differentiable. And now I want to look at the zero set, not only of f, I'll write it f bar, you'll see what I mean. Look at all the places on u and on the frontier of u as well, where, so I'm looking at all the z in the closure of u, such that one, the limit exists. Now we are in several variables, and we will see the limit does not always have to exist. So the limit of f of z, unlike the situation in one variable, exists and equal to 0.
So that should be z0 in the closure.
Sorry?
It should be the z0 in the closure of u.
Z0, yes, thank you. Yes. You look at all the places on both the sets. Of course, on the set, it just means that the function is 0. But you also look at the places on the boundary where the value approaches 0. It has a limit and approaches 0. Not only that 0 is a limit, is one of the limit points, but there is a limit and the limit is 0. And the theorem is that if the dimension, okay, now of this set is too big, then the function has to be constant. And what is too big is exactly, is at least the dimension of the frontier. So what is it? U lives in Kn. So Kn is R to the 2n. The dimension of U is 2n. So if this is less or equal than 2n minus 1, right? Which means in dimension, if we work in C, it just means that the dimension is at least 1, then f is constantly 0. Well, let's say that U is definably connected. Otherwise, we just have to then f is constantly 0. Sorry, I forget this. Sorry. Okay, so if you have on the frontier, of course, if you have inside a set of dimension, well, the largest dimension possible, which is not the full dimension, 2n minus 1. All my dimensions now, for now, will be real dimension, R dimension. When I talk about k dimension, complex dimension, I will say, whenever I say dimension, I mean the O minimum dimension. Okay, this will be strong. Later on, we will try to understand what happens when we take the intersection of an analytic variety, a k analytic variety, with another set, which is not necessarily k analytic. And when we'll try to understand this, this dimension, this will play an important role. When we try to remove singularities from analytic varieties, not only from functions. Okay. And the way one proves it is by going to fibers, really, and noticing that if this happens, then there will be a fiber where the dimension of this 0 set will be bigger than 0, so it will be at least 1 when you move in fibers. Then we apply the one variable identity theorem. We say, okay, so it has to be constantly 0 here. And if you know that there are sufficiently many fibers, then you will get eventually will cover an open set where this is 0. Right? So this proof just works in fibers using the fact that we have this identity theorem. I didn't put it here on the board, but in one variable. It's easy. If you know that, it's not hard to see why it will be 2. Okay, so this is 1, 2, property 2. Okay, now yeah. So I'm still working, let's say f from u to k is k differentiable. It's another 2. All partial derivative exists, and they are also k differentiable. All partial derivatives exist, and k differentiable as well. Okay, so if a function is k differentiable in several variables, then it is infinitely differentiable, just like in one variable. Three. And again, so here the definition is helpful because we don't need to prove directly something like that, but we can still, it's enough to prove things in, so you need to prove that the partial derivative is continuous, and this will be hard probably, if I remember correctly. And then to get the, it's enough to prove that it's differentiable in each coordinate, and there we can use the fact that we know the same result in one variable. So the definition helps when you try to prove that something is k differentiable, because it's a bit easier to attack. And again, we have this quasi-analyticity. I think this is how it's called. The map that send f, so a germ of f, let's say, germ of f at z0 to its formal power series of in several variables now. In n variables. So this takes value in the formal power series in, I guess, z minus z0 to be more precise. Then this map is injective because we have the identity theorem. I guess no, it's not only that. No, it's not because of the identity theorem, sorry. You show that if all partial derivatives vanish, again, you can apply the one variable fact. If all partial derivatives vanish, then you're constantly 0 in a neighborhood. So one can talk about the ring of germs at 0, and it's embedded in the formal power series of over k in z, in kz. So
sorry, Kobi? Yes. Jean-Philippe, do you hear me?
Yes, yes.
Yeah. Is there a way to characterize the formal power series which belong to the image of this map?
It depends on the minimal structure you work with.
Okay, okay.
Right, because if you work with just real closed field, then this will be just Poisson series or something, or it will be polynomials or things like that. If you work in R sub n, if you work in the Lipschitz-Robinson model, then you will get, this will contain, for example, all of RZ. Right. All the formal power series on Z. So this is a question that depends on the particular minimal structure you work with.
Okay, okay. Thank you.
Yeah. And now I'll put the removal of singularities, because as I said, this is the crux of the matter in terms of the strength of minimality is the ability to remove singularities for definable functions. So let me just list the results, which will be parallel or be generalizations of what's happening over there. Actually, it's a good question. What is, just in real closed fields or in the reals, what is the ring of germs in one variable even? Is it just a polynomial?
No, algebraic.
Yeah, but what is the power series at 0 of an algebraic set, which is algebraic function, which is analytic?
Well, I mean, it's all the power series that are algebraic over the polynomial ring.
Right. Okay. All right. Yeah, this
also
is
called the Henselization.
okay.
Yeah, well, it's the Henselian power.
So it's like the
polynomial ring localized at.
It's like the algebraic closure inside the formal power series.
Yeah, that's
okay. Right.
Yeah, that's
right.
one characterization.
Right.
And
right.
that's also true in several variables.
Right.
If you just have the purely algebraic structure.
Right. All right. So what is the setting? We'll have F. Yeah, let's have F from mu minus L, and I will say what L is. Let's have L closed and definable. Into K. All right, so we remove a set L, which could be a point, could be a bigger set, and we assume that this is definable and K differentiable for now. And now let's look at what we can say. So the corresponding thing to the first one, so here we allow the dimension to be at most 1, so codimension 1 inside C, inside K. And the same thing will be true here if the dimension of L is less than or equal, so the O minimal dimension to 2n minus 1, and F is continuous on U. So F is not only defined on X, so it can be, it has a, if you want a continuous extension to U, then it is K differentiable. Then F is holomorphic. So dimension 1 corresponds to dimension 2n minus 1 in general. Okay. If we allow L to have a smaller dimension, so what do I want to say? If, yeah, so if we take down the dimension, so it means the set where F is K analytic is bigger, but, and we allow, now we allow, if we do that, then of course this is true if F was continuous, but now we weaken this and just assume that F is bounded. Of course, once I put everything in U, so I should say bounded in a neighborhood of every point in L. Yeah, so I don't want that. So maybe it's better to say that L is a subset, is a closed subset of U. I think this is better. Because now I'm slightly worried what happens in the boundaries. If L could go out of the boundary, I don't remember if we allow that. No, I think it's not a problem because it's a locally. So, you don't need that. It's all local. So if it's what we need it to be bounded in the neighborhood of every point in L, bounded in around every point in L. Yeah, it doesn't matter. It's totally local statement.
Locally bounded.
Yeah, locally bounded around points in L.
Don't have to say that.
Then F is in the sense that it can be extended, differentiable on U. As unique extension. So this corresponds to Riemann removal singularity.
Around every point in L, you mean, right?
In L. Well, yeah, around every point.
Thank you.
Yes, thank you. Three, assume we even extended more the domain of analyticity, so we made the place we are not even smaller, which does not have a parallel here, of course. You don't have 2 minus 3. Then it turns out you don't need anything. You have enough continuity around L to just extend it directly. So F is, without any assumption, is K differentiable. And there's also, this corresponds to classical theorems on removal of singularities from very small sets inside, right? So this has no one-dimensional analog. This is a phenomenon of high dimension, which is a bit similar maybe to Hartog's theorem that special things happen for complex functions. Okay, now I'll put something else which we don't know of, and there probably is some analog of that in classical theory, but now I'm really here. We still didn't have anything because all the conclusions were K differentiability, so we didn't have anything like that. And this is actually something we worked quite a lot on. If dimension of L, so we are like in situation 2, but we don't assume that F is bounded. We don't assume anything with no further assumptions. Then I'll write something and then explain. F is Kmeromorphic. At every A in U, which means that at every point on this possibly bad set L, i.e. for every A in L, there is a neighborhood U sub A containing A and 2 definable K differentiable functions and not F I have, so GH from U A to K, which are definable and K differentiable, such that F restricted to UA is exactly G of Z divided by H of Z.
Are you then also assuming that H does not vanish at all at UA, or? The
G, you mean? No, H will vanish probably if it's this is like this picture. So this will be the result. This is the reason for having a pole.
Oh yeah, right.
But you can assume, yeah, you can always, because of what we know, you can always absorb the zeros of G into H. So I think that you can assume the G of A is non-zero.
Yeah, but now I'm a little confused.
All right. Right, so in our example, G was G, and H was Z minus Z0 to the end,
Yeah,
which of course vanishes.
yeah, you're right.
This is the reason for having a pole and not having differentiability.
But you have to assume something about H, for example, that it's not identically zero.
Right, right, of course.
Otherwise, it would be.
And I have to assume, of course, the F is not identically constant everywhere. Everywhere I'm assuming that F is not constant, otherwise H is not identically zero. I should say something, sorry, this is wrong. This is not on UA. This is not on UA because F is not defined on UA. I mean UA minus L.
Oh.
Sorry, sorry, of course.
In that case, maybe you should require that H is not vanishing at all on U0 minus L because now you.
Yeah, but yeah, so I guess you're right. Yes, you're right. Then for this to be definable, and H of Z is non-zero on U minus L. I agree. On UA. On UA. Now,
Suspicious now.
why? Why?
Well, anyway, there is a classical notion of meromorphic function, several variables, and it's something like that, but I'm not sure exactly what it.
No, I think it is
exactly what it was, but it's.
I think it's that. It is that. That it's a quotient in every point. It's a quotient of two analytic functions.
Exactly what does one mean by a quotient when the denominator is vanishing? That's what I'm worried about.
Right, but at least it makes sense. I'm not saying that I'm claiming that it's true, but at least this makes sense, right?
Right. Okay. Yes.
And I'll look it up again, but yeah, I think this is true as well. One thing to be careful of, which happens in several variables, I mentioned it, this need not happen anymore, right? We are not saying that there is a limit to the power to F as you approach Z0. So I mentioned it in another context. Note there might not be a limit to F of Z, even in K union infinity, even in projective space. Right? You could be, and the example is exactly Z1 over Z2 to Z1 over Z2, which is analytic K differentiable on C square minus Z2 equal to 0, but does not have a limit because when you approach along different straight lines, you will get different limits. So there is no limit to the absolute value of F, even if you go in the range into projective space. It doesn't help, right? It's not the problem at infinity. Then there are infinitely many, this is the point, limit points at 0, 0. Okay, so this phenomenon does not remain with us when you move to higher dimension, it just simply falls.
The assumption that L is closed, that's it for number 2.
The assumption that L is closed. No, actually, no, L let's assume L is closed. I can always just add the closure. It will not grow in dimension.
Right, so you don't need it for any one of them? Or
I assumed it for free for everyone, but I don't think we need it at any point, in any of them. Because you can always extend to the closure and the dimensions remain the same. So I believe there is no harm removing a little bit more, and by taking to the closure of L.
Now I just think too maybe when you need for two, but then you take a closure and something closure.
But it's only a local property, so you don't care. You go to a point Z0, and now you just care what happens near it. And if there it's bounded, you just extend it holomorphically, analytically here. Because the property of having a K differentiable extension is a local property. So you can just always restrict yourself to the area where it is bounded, and this will not, the fact that you have here boundary point will not have any harm. So that's why I removed, I thought first that L has to be absolutely closed subset of U, but it's enough that L is relatively closed in U. So the way it's written, I think this is correct. There is no problem if I'm not, unless I'm missing something. Notice that model theoretically, this is already gives some non-trivial information. This number 4, why? The property as I defined it of being holomorphic, Kmeromorphic at the point is not first order. Because we are saying there exists U, this is fine, no problem, but we say that there exist definable K differentiable functions in a neighborhood, and this is not a first order property a priori, right? Because we don't know how you get this this G and H, right? They depend on each neighborhood, and we are not sure why can you get them uniformly, but the result, well, first of all, because we prove the result in arbitrary structure, it will be true, but here we have a simple criterion to know when the function is meromorphic or not, and this is the size of the removal of the set that you removed. So as long as you know that the places on which the function is not holomorphic has dimension at most 2n minus 2, then it is, well, it's easy to see that it's if and only if, because the zero set of h of z, well, maybe it requires a little bit of work. Anyway, I'll write something and then it will be better. I might be jumping ahead a little bit, but so as a first definability corollary we get which again, if you're not interested in this abstract setting, you can think of it just in over the complex field. It's interesting by itself. If f of t is definable family of partial functions ft from ut to k, then the set of all t such that ft is Kmeromorphic, right? And for this, you don't meromorphic on U. And for this, you don't need to be a global function. It's a local, it's a property at every point. A and A is definable.
What do you mean by partial function?
That I don't know what the domain is. The domain is some subset of U to the K, of U. Still have, okay, so let me just say why it makes sense. What does this mean? So let's see if I can make sense of it, I hope. Then this will mean that for every A in U, there is UA containing A and definable K differentiable G H Okay, I see that there is some subtlety here that from UA to K, such that what I want to say now that for every Z, let's write it, and H is non-constant, non-zero. For every Z in UA, if H of Z is non-zero, then F of Z, so in particular, F of Z is defined outside the zero set of H equals to G of Z over H of Z. And we can, yeah, and we can add the opposite direction, but this is actually, I'm happy with that. But if not, we want, and if Z belongs to domain of F, then, well, then F is K differentiable. I guess this is the best way to write it. Then
when you write F, you mean FT or something? Or?
FT, yes, FT.
And the domain of FT, is that U minus some lower dimensional set, or is it?
I didn't say that, but it will come out of that. Yeah, it will come out because of the fact that it's definable outside the zero set of Z, and the zero set of Z, we know how to show that it has dimension at most 2n minus 2. So I'll write this, and I have 3 minutes. I will finish. Then F of Z is definable. So it's definable exactly outside the zero set of Z, and you can even say it's K differentiable outside. Okay, maybe I made my life complicated by writing it so general. Okay, so without having to go through each point and its neighborhood, etc., the only thing that we need to make sure is that F is K differentiable on its domain, and that the complement of its domain has dimension 2n minus 2. All right, so all of this. So the proof is just the set, right, that Ft is K Kmeromorphic. On U, actually, we could have done it on UT. It doesn't matter if and only if Ft is K differentiable, which is definable on its domain, Ft, and yeah, just the dimension of U minus the domain is small. Okay, all I'm saying is that this allows you to recognize neuromorphicity just by the places where F is not K differentiable. And then, of course, one can conclude from that maybe how many, I don't know, for example, I have to think about that. Do we need, I think it's enough to have actually finitely many functions like this. We'll have to cover U of T, but I'm not claiming it right now. I think we show it as well, that you don't need to work locally. You can actually cover the complement by finitely many open sets and finitely many expressions like that. All right, I'll stop here because of Alexei, and we'll continue on Wednesday.